Hey everyone, welcome to this episode of our quantum computing podcast. And last time we were actually on page number 15, and we had just ended our last video right here, just after exercise 1.2.11. So let's move on. All right, so this function, this conjugation function that we learned in the last video right here, which is nothing but a function that changes the sign of the imaginary part in the complex number, is actually bijective. Okay, so what is a bijective function? This function, the bijective function, is a function that is one-to-one and onto. Okay, now what is that? Let's go into some detail. So you know what, let's start with what a function is. A very basic thing. It's kind of a black box, right, which takes input and gives the output. Okay, so it's a mapping function. I mean, it's a mapping mechanism that maps input to output. Okay, so that's what a function is. But let me give you an example which is not a valid function. Let's say this function takes 3 inputs. Okay, and this input number 1 maps to some output. This input maps to maybe the same output, and this input maps to, let's say, some other output. But this input, the first input, also maps to some other output. Okay, so this input actually maps to 2 outputs, right here. This is an example of not a function. So function is a set of rules, or it could be just one rule, but basically it's a rule engine, right? It's a rule driven mechanism that maps input to the output. So if you provide the same input, it should give you the same output regardless of when and how you provide the input, right? So a function which is, let's say, a function that adds 2 to the input. If you input 1, it gives you 3. If you input 10, it gives you 12, right? So next time when you input 1, it should again give you 3. It shouldn't change it to some other number. So if you have input value is well mapped to 2 different output values, then it's not even a function. Okay, now let's go into what is one-to-one function. So we can use the same example. So let's say here we have an input which maps to some output, then another input which maps to some other output, and third input which maps to some other output. Okay, and there is one output which is not mapped. Okay, so this is an example of one-to-one function. Okay, so here each output value, okay, is a map to only one input value or not mapped at all. Or in other words, there is a one-to-one mapping between an input and an output, and it's possible that some output values don't even have any connection with the input, which is okay. So this is an example of one-to-one function. Okay, so this example right here is actually a one-to-one function, right? If you input 1, it will give you 3 because it's +2 function, and there is no other way to get to 3. You have to input 1. Okay, now if you think about a function that provides you an absolute value, okay, so if you provide -3, it maps to 3, and if you provide 3, it maps to 3. Okay, so in this example, -3 is mapped to 3, and 3 is also mapped to 3. Okay, or I should, yeah. So this is a valid function because there are two different inputs mapped to the same output. It's a valid function, but it's not a one-to-one function. Okay, so that's one-to-one function. What is onto function? Let's say it's a complementary, what you can say, complementary characteristic of a function. So onto function is, remember we had this extra output here. So in this example, or in this onto function characteristic, a function where each and every value of the output, let's say this function has 4 possible outputs, each and every, oops, where was I going? Yeah, each and every output is mapped. So for every output value, there is a corresponding input value. So that's an onto function. Okay, so this shouldn't be the case. Okay, it's a messy, so let me draw this again. Right, something like this. Right, so for each and every output, there is a mapping. All right, so this is an onto function. So for all possible output values, there is a corresponding input value. Okay, maybe take this as a challenge to think of an onto function. It's very easy, just think about it. But here the point is that if a function is both one-to-one and onto, okay, one-to-one and onto, then it's called a bijective function. Okay, so as you can see, this conjugation is one-to-one. So there is only one way to arrive to a certain output value, but also all output values have a corresponding has a corresponding input, right? Because we saw last time right here that the output that you get from this operation conjugations from this function is called the complex conjugate of that input, and vice versa. So those two values are complex conjugates of each other. We actually saw on page number 9 in the last video, and also a couple videos back right here, that this -1 plus I and -1 minus I were complex conjugates of each other. So basically you can go from, I mean, you can visualize, it's intuitive to understand that there is a one-to-one mapping, and also there is an onto property, which is for every output there is a corresponding input. Yeah, so two different complex numbers are never sent to the same number by conjugation. Yep. And for every number there's a complex conjugate, right? Or every number is a complex conjugate of some number, or other way around. But it definitely has one-to-one and onto properties. So it's a bijective function. Now, why that's important? So if there is a function that is from field to field, okay, C is a field. You might remember from the last video. So C is a field, and this conjugation is a function from C to C, right? It takes the values from set C, and the output is also in value, I mean set C. So if a function which is bijective and is a function that is from field to field and bijective, and also respects addition and multiplication, as we saw from this two exercises, then it's called a field isomorphism. Okay, so conjugation is a field isomorphism of C to C. Now, what is isomorphism? Well, one way to understand, this is just how I understand, is that it's a mathematical equivalent of the same in the quotes. Okay, so if there are two entities which are, they're the same or structurally the same and can be used in the context of equations and discussions interchangeably, and can also be derived from one another, right? You should be able to go from one entity to the other, and then it's called isomorphism. Okay, so it's just the mathematical way of saying they are quote unquote the same. Okay, so this is field isomorphism, but if you are let's say into graph theories, then there is subgraph isomorphism, but it's the same concept that if given two graphs, is one graph subgraph isomorphism, isomorphic of the first graph, and then how do you arrive? It's actually outside of the context of our discussion, but yeah, so this is what it's trying to say, right? With conjugation you can go from C to C and C to C, because see, and also respects addition and multiplication, which means that it's easy to go from one entity to the other and other to the first one with addition and multiplication, right? So that's what it is. Now I have read many pages of this book and some other books, and it's not terribly important to understand this in too much detail, but it's still important to understand this conjugation is a very, very important operation. All right. And I know we just covered one paragraph, and wow, 12 minutes have passed. How about we end here, and in the next video we will pick it up from exercise 1.2.12. Thank you.